After examining our star, the Sun, in our previous lecture, it's now time to turn our attention to investigating all the other stars. Many questions come to mind. How far away are they? How bright are they? How much energy do they produce? How hot are they? What are they made out of? And importantly, how do we know their masses? We're going to see that's actually very important to understand if we'd like to understand the stars. Well, we need to begin with distances. How do astronomers determine distances to stars? There's several methods, but there's one in particular that's really the foundation for all the other methods, a traditional method. And this involves a concept called parallax. Now picture for a moment, I'll show you a diagram, the Earth orbiting around the Sun. And as we look out into space, we might see a nearby star appear in a certain position relative to the background stars. Well, 6 months later, when the Earth has moved around its orbit, we look at that nearby star again, and it appears to have shifted position relative to the background stars. A little bit like if I was to hold my finger out here and look at it from this direction or from this direction, it would appear in a different spot relative to the background. Well, that tiny shift, again, is known as parallax. And essentially what astronomers do is they use a bit of simple geometry to measure that angle that we see the star shifting by and determine the distance. The closer the star, the larger the angle, and the farther the star, the smaller the angle. So this gives us a foundation with which to work. After we have established the distances of some stars by this method, we can then move on and use other more advanced techniques to reach out farther and get the distances to other stars. We next need to turn our attention to a couple of terms that are very important when we talk about the stars. Normally in everyday life we use the term the brightness of an object, but we need to distinguish brightness from something called luminosity. And the way we'll define these is to say that luminosity is the amount of energy or light that the star actually gives off, but brightness is what you and I see, what we perceive. Now right away you can imagine that that depends on several things. Number one, the distance, right? If the star is farther away, clearly it will not look as bright. But number two, it also would depend on the luminosity. If the stars, let's say two of them are at the same distance, well, if one is giving off more light, again, clearly it will look brighter. So how do we determine this, what the luminosity is based on the brightness? Well, again, we've already shown you how we can determine distances, and when we have the distance to the star, we can now apply a law that's well known and well understood called the inverse square law of light. And this law states exactly how light diminishes with distance. In other words, the intensity of the light is being reduced. And you know that if you were to stand nearby a street light at night, it would look very, very bright. But if you step back a few blocks, it would not look so bright. And yet the luminosity would stay the same, wouldn't it? So we again have a well-known understanding of how light diminishes. We call it inverse square because it, again, depends on the distance to the object. Now, I assured you we wouldn't do much math in this course. I'm going to show you just a few equations in this lecture. They really are optional. You needn't be concerned if they're not very clear to you, but for those of you who might like to look just a bit deeper, I'll show them just very briefly. And here you see the relationship between luminosity and distance and brightness. Now we could take this simple equation and we could rearrange it however we need to, depending what we would like to determine. So if you notice in the bottom, if we'd like to know the distance, well, we need to know obviously the luminosity, how much light the star gives off, and we need to measure the brightness. But if we don't know those, perhaps we'd like to determine luminosity, well, then we need to know distance and brightness. So the point is, if we know any two of these factors, we can determine the third. Let's do a couple of examples. Maybe that'll help us kind of grasp this a little bit. Think of two stars, equal luminosity. In other words, they're putting out the same amount of light, same amount of energy, but one is 3 times farther Well, what would their brightnesses look like? Well, our inverse square law tells us that we would take the 3 times, we would square that and put it in the denominator of an equation, and essentially then we would have 1/9 the brightness, 1 over 3 squared. So again, 2 stars equal luminosity, one is 3 times farther, it appears 1/9 as bright. Let's try another one. Let's say this time we have 2 stars at the same distance, but one appears 5 times brighter. Well, how do the luminosities compare now? How much light are they giving off? Well, if it appears 5 times brighter, this time we'll take the 5 and square it, and we would know that the star is 25 times as luminous. So again, the point being that astronomers understand this relationship between the brightness and the distance and the luminosity, and this provides a very powerful way for us to estimate, again, any of the 3. Well, what do we find in terms of stellar luminosity? Well, we could use watts, a common unit, but frankly it's far too small. The sun itself has a luminosity of approximately 10 to the 26th watts. And we're going to see some stars with a lot more than that. So the point is, rather than using watts, we're going to shift to a new unit. In fact, we're going to just use the sun as a unit of luminosity, and we're going to say that a particular star has this many solar luminosities, or this many. Well, again, we see a wide range. What do we find? We find that some stars could be 1,000,000 times the luminosity of our sun. Hard to imagine that. Others, at the low end, could be 1/10,000th the luminosity of our sun. Very, very low luminosity. So a wide range, 10 orders of magnitude of luminosity among the stars. We'll be back a little bit later to look more closely at those various types of stars and why some are so luminous and some are not. Now let's move on and discuss the temperatures of the stars. How could we possibly know the temperature? We're certainly not going to fly out to the star and stick a probe in it. Well, again, we turn to a few laws of physics that are well understood. And these laws are based, again, on light. To start out, what we're going to do is take the light from a star. Astronomers would take the light from the star, perhaps passing through their telescope, and they would break that light into a rainbow. Perhaps you're familiar with the term spectrum. We take the light, we break it into this spectrum, and that spectrum is showing us different wavelengths of light. Now, you and I are familiar with these in the sense that you and I see perhaps red light, or yellow light, or blue light. Well, red light is a little bit longer wavelength, and yellow is kind of a medium wavelength, and blue light is a shorter wavelength. Now later on we'll see that these wavelengths extend beyond what human eyes can see. But the point is this: we break the light into a spectrum, and our instruments allow us to determine the intensity of the light at those different wavelengths. So you can see in a diagram here that we might have the spectrum showing us the different wavelengths, and different wavelengths may be more or less intense. Well, there's one wavelength in particular that's very interesting to us, very important to us, and that's the peak wavelength. In other words, where is the light most intense? Where does it have the greatest intensity? If you look at our diagram here, you see that it's really, in this instance, in yellow light. So this particular object, if it was a star, would appear somewhat yellow to your eye. That's where most of the light is. There's not as much red or not as much blue. Well, here's the key in terms of temperature. The temperature of the star can be determined if we know the peak wavelength. How do we do that? Well, we have a very simple equation. Again, nothing to be concerned about, but on the other hand, it does give you a deeper insight. Let's go ahead and take a look at our next diagram here, and we see that equation called Wien's law. And you see, if you look closely there, the T stands for temperature. We have simply a number on the top, 2.9 times 10 to the 6. That's approximately 2.9 million. We're going to divide that by the peak wavelength. Why that number? Well, it's just related to the particular unit of wavelength we're going to use. And we're going to use, for most purposes, astronomers will use nanometers, 1/1000th of a meter. Okay, so you look now at this particular diagram, you see a little different view of the spectrum. We haven't colored in all of the colors, but you do get the sense here. And what we're doing is showing three different stars. You see one with a tall blue peak, you see one with a yellow peak, and one with a red peak. Well, the blue is indicating that this is a hotter star. Notice how its peak wavelength is towards the left. Shorter wavelength. Well, if we take that particular number and plug that into our equation, we're going to get a higher temperature. On the other hand, our red curve for our cooler star, we take that peak wavelength and plug it in that equation, we're going to get a lower temperature. So what a remarkable equation we have here that really allows us to know the temperature of a star by analyzing its light. Looking for that peak wavelength tells us the temperature of the star. This then allows astronomers to go on and determine even more about stars. Let's move on now and talk a little bit about the size of a star. How big are they? They just look like points of light to us in our telescopes. How can we possibly know their size? Well, let's go back and think for a minute about luminosity. Luminosity, we said, is how much total energy the star is giving off. And again, think in terms of the star is giving this off from a spherical surface. So light is being emitted in all directions, isn't it, from this star? We may only see a small fraction of that. Then think about what we just discussed about the temperature of the surface. Well, isn't temperature the amount of energy that is coming out of a particular area of the star? Let me show you another diagram here where you see that. One small area is shown cut away. And the point is this: if we know the total energy, and if we know the energy in one small area, we can figure out the total area of the sphere of the star. Well, once we have that total surface area of the star, that can lead us to the radius of the star, which essentially is 1/2 the diameter, as you can see here. So in other words, we use luminosity and we use surface temperature to tell us the size of the star. What, again, a remarkable way to be able to determine the properties of the stars. Using these correct units will enable us to figure out the size of the star. Well, what about stellar composition? What are the stars made out of? How could we possibly know that? Again, we're not going to be able to fly out there and get a sample and bring it back. No, but we, again, have many clues in the light of the star. Now, many years ago, scientists did some experiments here on Earth. They took elements in the lab, they heated them up, and by, again, taking that light and breaking it into a spectrum, they noticed that the spectrum had certain distinct lines in it. Some of them were darker lines and some of them were brighter lines, but they noticed pretty quickly a correlation. In other words, depending on the element, if you heated up a certain element and looked at those lines, they had a very unique pattern to them. And so surely you could look at that pattern and say, I know what that element is. Well, we can do the same thing with starlight. We can take the light from the stars, break it into a spectrum, we can look for those specific lines, and we can identify the composition of its elements. Overall, we find out that it's primarily hydrogen and helium, but other elements as well, oxygen, neon, and so on and so forth. So yet again, a remarkable way for us to be able to determine a property of stars without ever leaving Earth. Take the light, break into a spectrum, look for that unique pattern of lines, and that will tell us the composition. Now, scientists originally measured those lines, their specific, very unique wavelengths here in the laboratory on Earth, but often we'll look at a star's spectrum and we'll notice perhaps a pattern of lines, and they are shifted slightly. What does that indicate? Well, without going into too much detail, it indicates the motion of the star. In other words, if the star is moving slightly towards us, the light it emits, the wavelengths of the light are going to be slightly compressed. And if they're compressed to a slightly shorter wavelength, they're going to appear shifted slightly to the blue Conversely, if the star happens to be moving away from us, the wavelengths of its light will be slightly stretched out or longer, and they will shift slightly to the red. Now this phenomenon you may have heard of is called the Doppler shift, and it allows us to measure the velocity of the star, whether it's moving towards us or away from us. We're going to see in just a minute that's a very useful, very important property as well to be able to determine the velocity of stars. So again, astronomers look out at the stars, they notice these various spectral lines, and they begin to understand the elements they're composed of. Well, in the early 20th century, they began to essentially classify the stars into various categories. And interestingly, they found again different stars had different elements, but at some point they began to realize that there was a sequence of stars, if they were arranged according to these lines, that indicated temperature. And as we'll see in a future lecture, now we have various categories of stars that we know are a certain temperature and a certain composition. So, we've already seen much about the various properties of the stars that we can determine based on the light that we receive from them. Well, we have one more very important property of stars we need to determine, and that's stellar mass. We need to know how much material is in a star. Now surely we can't fly out into space and weigh a star, can we? In fact, we don't really use weight. Weight is more a matter of how strong gravity is pulling us down to the Earth. Again, mass is how much material there is. So how are we going to determine mass of stars? Well, the key really is using gravity. If we understand gravity, we'll be able to determine the masses. You might know that Isaac Newton was the first one to get a first good idea of gravity. And Newton was able to develop a method that allowed astronomers eventually to determine the masses of stars. How did he do that? Well, I'm going to show you one more equation. And again, don't let it concern you, but for some of you it will provide a little deeper insight. Essentially, Newton said that if two stars were orbiting each other, gravity, of course, would hold them together. And the gravity would determine, number one, how far apart they were, and number two, how long it took them to move around each other. So we need to measure these two properties. The period of time they take to orbit, we simply call that the period, and we designate it by p. The distance between them, we're going to designate, we'll call that separation, and we'll just designate that by the letter a. So here you see an equation showing you this relationship. The mass of the first star plus the mass of the second star can be determined by measuring these two quantities. Well, how are we going to do that? Well, back in Newton's day, and as the decades went on, astronomers became proficient at looking up in the sky and seeing what we now call binary stars. In other words, stars that, again, are bound together by gravity. Now, there's three different types I'm going to touch on briefly. And when we are finished, we'll step back and see how we use binary stars to determine masses. Number one, we have something called a visual binary. And it's very much what it sounds like. You simply look through the telescope or take a photograph and you see two stars. Beautiful image of these binary stars. We're going to look how we measure that. Then after that, we'll talk briefly about an eclipsing binary star. And we'll finish up with the third type, or spectroscopic binary. Let's see what each of these is. In our first diagram, we notice again a visual binary. Now stars, it turns out, are separated by great distances, and it takes quite a bit of time, in general, for them to orbit around each other. They may not orbit as quickly as the Earth goes around the Sun. So the point is this. Over the years, astronomers would carefully measure the positions of stars as they orbit each other. We look for the period of time it takes, and we look for the distance between them. Those are the key things that we need to observe and measure to put back in that equation to tell us the masses. Well, one way is, again, simply that, to watch the stars move and carefully measure their positions. That's very tedious work, very painstaking work. But during the late 19th, early 20th centuries, astronomers did that and essentially used that technique to determine stellar masses. In time, another method became available, And that happened to be stars that we knew to be orbiting each other, but perhaps we couldn't see them very clearly. How did we know that? Perhaps they were closer together. Well, if we watch the total light from the star, it might be at a very constant level, but at some point it would dip down for a short time and dip down for a short time periodically. What's going on? Well, envision two stars circling each other. From your point of view, one star blocks the lights of the other. So the point is, we normally have the light of both stars as a maximum amount of light, but when one star blocks the other's lights, well, this is when we see that dip in the total amount of light. You can see in our diagram here. If we look for the time period between the dips, we can determine the period that the stars are orbiting each other. So this is just a little different way to obtain the period of the orbit of the binary stars. We have one more way. This is termed a spectroscopic binary. What does that mean? Well, you can sense that that word spectrum is in there, and yes, it implies, again, stars that we maybe can't see clearly individually, but we know there's two there. How do we know that? Well, remember we discussed the fact that a star has a certain spectrum with a certain distinctive pattern of lines. So let's imagine that one star has a pattern of 4 lines and one star has a pattern of 2 lines, for simplicity's sake. What if we looked through our telescope or took a picture, or really a spectrum, of what we thought was a single star, but we saw all 6 lines? We could properly assume that there was probably 2 stars there. Well, do you recall a few minutes ago we discussed that if the star was moving towards us, those lines would shift slightly towards the blue end of the spectrum? And if another star happened to be moving slightly away from us, it would shift to the red end of the spectrum. So I think you see where I'm going here. If we noticed the spectral lines of what we thought was one star, and 2 of them were moving this way and 2 of them were moving this way, we could safely assume that we have 2 stars, one moving towards us and one away. And at some point, the motion might reverse itself. 2 lines would move this way and 4 lines this way. This would be when the stars now are moving around their orbit this manner. So the point is, we may not even see both stars, but those distinct spectral lines would tell us there's 2 stars orbiting each other. Well, couldn't we take and measure the amount of time that one complete cycle takes for the lines to move? And wouldn't that indicate the amount of time for the stars to orbit each other? So again, I think you can see we can determine the period of time needed for the stars to orbit each other. So we have several ways to measure the period of time the stars orbit. But the other piece of information we needed is the distance between them. How are we going to figure that out? Well, let's think about that for just a minute. If we notice, again, the time period that the lines are moving, we can get a pretty good idea of the velocity of the star. How much does it shift? Do they shift just a little bit, or do they shift a great deal? That would tell us the velocity of the star moving towards us or away from us. If we also have that velocity and we have the amount of time or period, we can determine the distance between by a simple mathematical relationship. The orbital radius equals the velocity times the period divided by 2 pi. So we can get the separation of the 2 stars. And again, this is that second measurement that we're after. Once we have that separation and that period, now we can go back to that equation we saw earlier and plug those numbers in with the correct units. We can determine the masses of the 2 stars. In a few cases they could be equal in mass, but in many cases they're not. One may be more massive than the other, and there are ways to determine that as well. But the point is, we have a way to determine the masses of the stars. If that was just a bit technical for you, feel free to pause the video and go back and look at some of those slides and piece that together. but I think you can see it's a powerful method that astronomers can use. We've been able to determine stellar masses to great accuracy now. What have we found? Well, again, quite a range, actually. And again, we're not necessarily going to use kilograms. That's far too small of a unit. But once again, we'll turn to the sun, and we'll use one solar mass, approximately 10 to the 30th kilograms, as its own unit. What do we find? We find some stars with 150 times the mass of our sun. We find others that are a mere 8% the mass of the sun. So again, a tremendous range of masses, and again, we'll be back to discuss that in more detail in future lectures. So I think you've seen some of the very powerful, ingenious, remarkable ways that astronomers can determine the properties of stars. What appear to be tiny points of light in the sky are very amazing bodies out in the universe, aren't they? Well, let's go ahead and do our summary and make sure that we're clear on how we did some of these things. Number one, we started out with stellar distances, didn't we? And we learned about this parallax effect. In other words, if a nearby star is viewed from different perspectives in Earth's orbit, we see it shift slightly. The amount of the shift can easily tell us the distance relative to the background stars. Number two, we looked at stellar luminosities, didn't we? And we were very careful to distinguish the difference between brightness, that is what we see, and luminosity, which is the amount of light that the star gives off. How do we determine this? How do we correlate these, so to speak? Well, we saw the key really was the inverse square law of light. Clearly, the farther away the star is, the dimmer it appears in brightness, but its luminosity didn't change, did it? And we understood how it changes with that inverse square of distance. How about stellar temperatures? Well, again, we looked at a single spectrum of a star. We took the light and broke it into that spectrum, and we looked for the peak wavelength or maximum intensity of light. And that wavelength in a certain unit can be put right into a very simple equation to give us the temperature directly. So nature was very kind to us there, gave us a very easy way to determine stellar temperatures. You'll recall Wien's law. How about stellar sizes? How big are they? Well, if we compare luminosity and temperature, we can find the radius of the star, because we're able to determine the surface area of the star, and that leads us to radius. How about composition? We're back to the spectrum again, don't we? We look at that spectrum, we notice those distinct, unique lines, and based on work that's been done in the laboratory, we can point at those lines and say, well, there's hydrogen or helium or oxygen. It's almost like a fingerprint, so to speak, that we can identify in the stars. Finally, solar masses were a bit more complicated, weren't they? We needed to measure two various parameters. Number one, the distance between two orbiting stars, and number two, the amount of time it took for them to do that. And we saw several ways to measure the amount of time or period of the star's orbit. We could just watch visually as they do that over the years, very tedious but workable. We could also look at the eclipses. As one star blocks the light of another, we see a dip in the light. Well, the time between eclipses tells us the period. And we also saw that we again can look at the spectrum and identify spectral lines in each star as they're gradually moving over hours, days, weeks, months, and figure out how long it takes them to move. Once we have the amount of time or that period, we need the distance between them, and we saw how that could be determined as well, didn't we? This gives us the masses of the stars, and as you'll see in future lectures, that's a very important piece of information. So we've really learned a lot, haven't we, on the properties of the stars, and now we're equipped to again move on and not only look at stars as they are today, but in our future lectures we're going to trace how stars form, how they live, generate energy, how they change, and ultimately how they die. So I look forward to seeing you in our next lecture.